What is probability?
Well, if y'all have had me in 120 before, you know probability is basically assigning a number to a prediction.
That's all there is to it. As soon as I can get the handy dandy whiteboard to pull up. Is it not going to pull up? There it is. Probability, and this is you said chapter 7. What sections do we cover? 7 what?
7A, B, C, and D.
B, C, D. So it's everything?
Not D.
Just D.
Just D?
Not D output either.
So A, B, C, and E?
Yes.
What's the title of D?
Oh, wait, of E?
Yeah, of D.
Oh, really?
In the book, what does it say? If you don't know,
Hold on.
just curious.
Assessing risk.
I don't need to go over that. Probability, this is a Hubertism definition. Probability is assigning a number to a prediction. We've all done this before. Let's say that, and I give y'all this example in 120 all the time. Let's say that you're on Wild Hog Road and you've got an 8 o'clock class, and this is Pendleton High School, and this is 24, and double bridges are right here. That's the double bridges. 85 is up here. Okay, so you going, and it's about 15 to 8, and you're turning on the Wild Hog Road at 15 to 8. So 7:45 a.m. And you've got an 8 o'clock class at Pendleton. Okay? Now, it only takes 10, 12 minutes to go down Wild Hog Road. I know that because I've done it before. And it only takes 10 to 12 minutes to go down Wild Hog Road from here to there. But anytime you got 15 minutes to get down Wild Hog Road and you got an 8 o'clock class, who's going to be in front of you?
Granny.
The little granny club. Little blue-haired ladies club. And she's going to be right in front of you, and she's going to go 35 miles per hour. And she has that cruise control set on 35 miles an hour. Whether she's going down a hill or whether she's going up a hill, she's going 35 miles an hour. You get to the end, you're mad, and there's a lane. Let's see. I'm going to blow this up a little bit. There's 2 lanes right there. One right there and one right there. And there's red light. Well, right about between Pendleton High School and that lane, you're going to get right about here, and little old lady is right about there, and you're going to say to yourself, please turn right, please turn right, please turn right. And then she's going to get here, and guess what she's going to turn? What blinker is she going to turn? Left. How'd you know that?
She's granny.
How'd you know that? You just predicted the future. Why? Because how many times have you gotten behind the little old lady? And when, well, there's something else too. If somebody is on Wild Hog Road, they're not going to turn right and go back towards LaFrance. They could have done that through Centerville Road. You know, they could have done that. So, geographically, they're not going to turn right. But most of the time, you know that if you get behind somebody going 20 miles an hour and they come up to a red light that turns left or right, they're going to be turning whichever way you're going because that's your prediction. And a lot of people say, well, you can't use that as an example. Well, I'll use another example if I can figure out how to work this page. Got a pasture. And you got a holding pen. Got two pastures. Here's two pastures. Right there. And you got a holding pen right here. That's where you work your cows. And you got a fence, a lane right here. That's how you get them in the little holding pen. So you got a gate here. And you got a gate here. And let's say you got other pastures around these two. And let's say there's a gate down here. And it's open. So there's an open gate down here. There. And let me open this up because I got to open that one up. That one's open. And open this one up. That one's open. And you run in the cows. Let's say that you got a pasture over here, and this is a pasture, and let's say that the pasture right here, and the cows are in this pasture right here. Okay? And you open this gate right here. There's the gate. And you run them into this pasture right here. Okay? Which gate do you want them to go to? You want them to go to this gate. Which gate are they going to go to? They're going to go straight to that one. How do I know that? I can't predict the future. I know that because that's the way things roll. Just like the little old lady turning left, I know that if this gate is open and this gate is open, 9 times out of 10, those cows are going to shoot for this gate right here. Because that's not the one I want them to go into. And that's the way probability works. Can I predict the future? No, I cannot predict the future. And I'm going to put that right here. We cannot predict the future. Horse buggy. But we can assign a number based on history, math, or simulations. Why can we not predict the future? Well, if anybody could predict the future, what's the first thing they should do? Say again? Go to the lottery. Go play the lottery, and then after they win enough money to travel, hit every gambling casino that they can hit. So, if anybody ever says that they can tell the future, what's the first thing that you should ask them?
You gotta go buy me a lottery ticket.
That's it. Nobody will take you up on it because nobody can tell the future. Now, you have all these people that can take tendencies and patterns, and they can say, okay, I bet this is going to happen, or I bet this is going to happen. And that is not telling the future. That is analyzing something and putting a number to a prediction. That is not telling the future. All right, telling the future, you've all seen Back to the Future 2, right? What happened in Back to the Future 2? I think it was Back to the Future 2. What did Biff do? Biff was a billionaire. Why was Biff a billionaire?
He stole the almanac.
He stole the almanac. What kind of almanac? Sports almanac. That's predicting the future. He took that almanac and he predicted the future because he knew the future. Now, there's only one way to tell the future, and that is to go into the future, see it, document it, and come back to the present, and then you can predict the future. That's the only way to do it. Time travel. There is nobody that can predict the future. Remember Chloe? Was it Chloe on TV? I can tell you who your soulmate is. I can tell you where you will be in 15 years. Why did they throw her in jail? Fraud. You can't tell the future. First thing I would do, 1-900, Chloe, yeah, you tell the future. Give me those 5 numbers. Huh? Oh, well, it doesn't work that way. That's the first thing they'll say. And I need to know a little bit about you before I can tell you. No, just give me the 5 numbers.
That's right.
They can't do it. So, history. History of you riding behind the little old lady. The history of me getting up cows and the cows going the opposite way that I want them to go. Math. Taking math, like the cards. We're going to do that. Simulations. Running the simulations. Practicing it over and over and over until you get to where you can actually predict what's going to happen. Now, what is probability? Well, we just did that, but what is it mathematically? Probability of an event happening. That's the way you write it. Probability of A. That is probability of an event happening. Now, I don't write probability of A. I write the probability of that event. Like the probability of picking a king in a deck of cards. Now, in order for you to pick a king, a deck of cards, you've got to know how many cards you're talking about. You've got to know how many suits. You've got to know how many different cards there are. If you don't know any of that, you can't do this. But anytime you have an event happening, it's the number of times something happens over the number of times it can happen. Now, I know that sounds kind of redundant, but how many cards are there in a deck of cards? We're going to get to that later. 52. So you can pick any of the 52 cards with one draw. But how many kings are there? Well, there's 4 suits, so that means there's 4 kings. So the number of times that you actually pick a king is 4. And that is your probability. Yes, it can be simplified. But let's talk about simplification. How do you simplify this? Well, we don't care about fractions too much, but fractions is one way, reduced. And the other is decimals. Now, both of them are going to be between 0 and what? 1. 0 and 1. So any improper fractions do not work. Any number, decimals over 1 will not work. Anything between 0 and 1. Just remember your rich sizes. 1/2, 9/16, 5/8, 11/16, 3/4, 13/16, 7/8, and 15/16. Those are all rich sizes between 0 and 1. You could say 1/4, 3/8. 1/4 is about as small as you can get. 3/8, 7/16. All of these rich sizes are between 0 and an inch. What about 5/2? Well, 5/2 is not even considered because 5/2, if you change it into a decimal, is 2.5. 2.5 is above what? 1, so it doesn't work. So, 0 is not likely at all, where 1 is very, what? Likely. So 0.5 would be somewhat likely. And that little scale is in your book somewhere. What page is that scale on? Anybody see it? 0 to 1.
It's on page 412.
412. Now, again, we're going to start with a deck of cards. Anybody ever need to know the different decks of cards or different numbers in the deck of cards? You can always pull up the Soldier's Bible. I showed y'all this in 120, didn't I? Yes, no, maybe, yes. Okay, well, somebody remembers. At least one person remembers. Yeah. I think it's called the Soldier's Bible. A Soldier's Bible deck of cards. Well, you gotta find it. But anyway, just a story about a deck of cards. I can't find it right now. But anyway, how many cards are there? There's 52 deck. There's 52 in a deck. There's 52 weeks in what? Year. And it goes through all of that. I don't know where the... I'm trying to find it. Hold on a minute. There it is. Oh, good gracious. Come on. There's nothing worse than computer-generated music. All right. And you go right here. You see the aces, one god. Ace means what? 1. 2 represents parts of the Bible. 3, I'm not trying to convert anybody. I'm not going to pass the offering plate or anything. But that's how people remember. There are 52 cards in the deck, 52 weeks in a year. 4 suits represents the 4 seasons. Each suit has 13. There's exactly 13 weeks in a quarter. A lot of people don't know that. You know, that kind of stuff. So anyway, that's the deck of cards. So let's go back to our handy dandy whiteboard and write down a couple of things, especially 52 cards in the deck. 52 cards in a deck. Now there's also the big joker and the little joker. Now that's usually, those are not used in card games, but some of them are used. But 52 are regulation playing cards. 54 is non-regulation. There's 2 cards, and then there's the instruction card nobody ever uses. So technically, if you want to say technically how many cards are in the box, there's 55. Okay, maybe 56, depending on if they put another card in there for some reason. There's 54 with the big and little joker. All right, but usually you do not use the big and little joker, so there's 52. There's 4 suits. There is the hearts. There's the diamonds. Dang old girl's best friend. Dang old spade. And leave me alone. And puppy feet. I'm sorry. Clubs. Okay? Looks like a piece of broccoli. All right, here's the pen. Come on up here and draw. All right. So there's 4 suits, and like I said, 13 in each. There's 13 cards in each. There is the ace, the 2, 3, 4, 5, 6, 7, 8, 9, and 10. Those are the number cards. Then what is there? Jack, king, queen, which are the what? Face cards. So there's three types of cards. There's the ace, there's the face cards, and then there is the number cards. And all of them together is equal to 13. Okay? So, if I ask you the probability of an event happening, let's say the probability of a face card. This thing is not working today. Probability of a face card. Well, there's 3 face cards in each suit. And how many suits are there? 4. So 4 times 3 is
12.
over
52.
12 over 52. And you reduce that and put it in terms of a decimal or a fraction, depending on what the directions say. Always reduce. Decimal or fraction is basically what the directions say. How about, what is the probability of an even card? Well, you go over here and count your evens. So take your handy dandy highlighter and let's see what's even. 2, 4, 6, 8, 10, and Jack, King, Queen. What are they? Tens. So 1, 2, 3, 4, 5, 6, 7, 8. What's 8 times 4? How about 32? So that'd be 32 over what?
52.
Reduce and answer accordingly. So the probability of something happening is the number of times it can occur over the number of times that any event can occur. Just remember your large number is going to be on the bottom. Now I can do it with a deck of cards, or I can do it with a die. What is a die?
1 dice.
One of the dice, like on a Monopoly board. So if I ask you, what is the probability of rolling a 6? What is the probability of rolling a 6? 1 out of 6. There's 6 sides. 1, 2, 3, 4, 5, 6. The probability of rolling 1 6 is 1/6. What is the probability of that? What is the probability of rolling an even number? 3 out of 6. What is the probability of rolling a 7?
Negative.
0. Don't happen because there's no 7 on it. That's the trick question I put on the test. People miss it. All of these probabilities that we went over is what I call Mayberry probabilities. Now, Mayberry probability is not going to be in your book. It's not going to be in any book. This is what Hubert called it. Why do I call it Mayberry probability? Well, what is Mayberry? Yeah, no, yeah. What is the Andy Griffith Show?
A simple way of living.
Simple way of living. You getting there?
The easy way.
It's what?
The easy way.
The easy way. What do some people consider it?
Back in time.
Back in time. Y'all not getting warmer at all. You just stay in the same temperature. Huh?
Old-fashioned.
Old fashioned. Yeah,
The
that's
best way to live.
best way to live. Okay, you're getting warmer. Getting warmer.
The best way to do it.
Best way to do it. You're still getting
I
warmer.
don't know. Tell us.
Starts with a P.
Passion.
That's how you do something.
Persistence.
P-A-R.
Fast.
R. P-A-R.
Pride. No, that's
P-A-R is paradise. Why do people like Mayberry?
This is simple and
It's
lovely.
paradise. It's the modern day utopia. Which means that everything is what?
Simple.
Perfect. Everything is perfect. How many riots did they have in Mayberry? None. How many killings did they have in Mayberry? None. How many rapes did they have in Mayberry? None. Although Miss Ellie did not like working with Andy because I think he perved on her a couple of times.
In real life?
That's why she left. Yeah. I don't know if he
Don't
perved
tell me
on
I'll
her or
never be able
what.
to watch that show this thing.
Yep.
I
She
love
was
that
only
show.
on 7 episodes, and she was supposed to be his long-time girlfriend, but she quit. And she was the hottest
Andy.
woman.
I'm ashamed.
Yep. Evidently, he was perving on her. That's only because she said in an interview that she will not speak on it. She was asked, why did she leave the show? And she said, I didn't feel comfortable working with Andy.
Wow.
Now, why else would you say something like that?
Yeah.
So,
Oh.
anyway, Miss Ellie, that's what my mother looked like when she was young. Miss Ellie, that's what my mother looked like. In fact, you could take a picture of my mother in the 50s, early 60s, late 50s when she was 19, and she looks just like Miss Ellie on the show. Look like sisters. Anyway, what's that got to do? Mayberry probability is the perfect probability. It's the probability that nothing interferes with. So all of these right here. And what was the probability of a king? 4 out of what? 52. What's the probability of a face card? 12 out of 52. What's the probability of an even card? What'd you say? 32 over 52. All these are Mayberry probabilities. Why? Because nothing can mess with them. Nothing can hinder them. Nothing can affect them. You are counting the number of face cards and you're putting it over the number of what? Cards.
There it is.
So that is the perfect probability. Nothing can touch it. Nothing can influence it. Nothing can alter it. Well, what's the other probability? Well, there's the actual probability. And that's why I wanted to bring the cards. I got like 15 decks of cards home. I forgot them.
I got a deck of my cards.
Well, go get them. But I call it physical probability. Are you going to see it in your book? No. In your book, it's probably called the theoretical probability and the classic probability. That's what it's probably called. I don't care. Physical probability is the probability that you actually get when you try. How do you spell probability? Is that right?
You wrote it too many times.
All right. The physical probability is the actual probability when you try. All right? When you try. The formula is the same. The formula is still the number of times something happens over the number of times it can happen. All right? Let's say that you want the probability of a king. And you said that was 4 over 52. Well, let's say you go out in the parking lot and you get Miss Holmes's cards and you shuffle them up 20 times or whatever, and you shuffle them 10 times, and each time before you shuffle them, you pull a card, you put it back in, you write it down, put it back in, shuffle them again. Pick one. And let's say that you pick 10 times and you got 2 kings by picking a card each time you shuffle. Put it back, shuffle
2 or 3 times. Pick a card. And you'll say you got 2 kings. Well, what's that probability? 1 over what? 5. Somebody take a calculator. What's 4 over 52?
1 over 13.
Huh?
1 over 13.
No, what is 4 over 52? Give me a decimal.
Oh,
3 decimal places.
4 over 52.
Yeah.
0.076. No, I don't know.
Okay, I just heard 5 different numbers.
0.077.
Heard 2 different numbers.
Point
How many
0.
decimals you want?
76.
076.
Do you want how many decimals you want?
3.
Well, that 6 should be the 7.
077.
Yes, because there's a 9
Okay.
on that 6.
077. All right, what's 1 over 5? 0.2? They're supposed to match. What's wrong? Why the 2 different numbers?
Because you stuck it back in instead of redo it.
No, the physical probability is always going to be different from the Mayberry probability. Always.
That's perfect life.
Unless you do it a bunch of times, which is called the large number rule. See if it's in your book anywhere. Large number rule, or the rule of large numbers, or the law of large numbers. More times you attempt. Anybody found it? Is it in there?
It's what 7C is all about. The law of large
7C. Okay. Then what page 7C start on?
It starts on page 437.
437. More times you attempt, the closer the physical probability approaches the Mayberry probability. There was in about the 10th edition of Triola, there was a big write-up of the law of large numbers, and it was a real good write-up. Why they quit putting it in there, I don't know, but what do they call it? Law of large numbers, or the large number law? Law of large numbers. Triola, 8th edition. I think it was the 8th edition. Let's see what this one says. They had a real good write-up about. Let's see. No, that ain't what I'm looking for. It was in the book. Go away.